We're going to look at the definite integral now. And one of the applications of the definite integral is total change. Before we've looked at the indefinite integral, and the indefinite integral gave us a function. We took the antiderivative of some function f of x dx, said that was equal to capital F of x plus c. So what we got was a function. Now the definite integral gives us a number. So that when we talk about the definite integral telling us a total change in something, that is a numeric value. We start at some point, we go to another point, and the definite integral tells us the change between those 2 points, the total change. So let's look at an example and then see a way that we can write a definite integral. Now up here we have the table from our problem where we're given the rate of change function in terms of numbers. It's the rate of change of revenue. So when 20 caps are sold, the change in revenue is $8 per cap. By the time 40 are sold, the change in revenue is only $6 per cap. So the change in revenue has gone down a little bit. And as we see, by the time we get over to 120, the change in revenue is going down even further. Now remember that this is just revenue, it's just a rate of change, and what we want to do is to estimate the total change in revenue, in income. And to estimate the total change, we're going to use this data. Now, we have the interval where it was $8 per cap was the change in revenue, and then it decreased to $6 per cap when we went from 20 caps to 40 caps. So on this interval, 20 caps were sold. And we have a choice as to whether we say, well, over that 20 caps, is it 20 times 8 or is it 20 times 6? Let's choose the left end point of the interval, and that's the one we're going to work with. So when revenue changed $8 per cap times $20, that'd be $160 was the change in revenue over this interval. And we'll do that for each interval. And each time I'm going to choose the left end point to work with, the next 20 units, and so on. So I'll always look at the interval and I'll choose the left end point each time as I work with my numbers. Be sure that you look at the example that's in the lesson so you can follow a little bit better what we're doing here. So if you haven't looked at the lesson, do that first. So let's see. This is the change in revenue. If I'm looking for my revenue, not my revenue, my total change in revenue. Better write that whole thing down here. Total change in revenue. What I want to do is take my $8, which was the change at this point, times 20. This is dollars per cap times number of caps, plus 6 times 20, plus 4 times 20. This gets me to 3 intervals, plus on my next interval, it's 2 times 20. On this interval, it is 0 times 20. And on the last interval, we have -2 times 20. So the total change is the sum of all these numbers. So I have 160 and 120 and 80 and 40 and 0 and minus 40. Add all those up, we end up with 360, and that is in dollars, and that is dollars of total change of revenue. And another way to say that is that revenue increased $360 over the time period that we sold from 20 to 140 caps. revenue increased $360. This is not total revenue. This is the increase in revenue. So if you think about it, we may have started at $800 revenue. So that was what the revenue was, $800. And this says we've increased $360. So if you add $360 to that, you end up with $1,160 as the revenue at the end. We don't know where we started. We don't know where we ended. We just know that revenue over that interval from 20 to 140 increased $360. So I went the interval from 20 to 140, and I divided it up into subintervals of 20 each. Now, I can write all of this as a definite integral, but this is the way we would work it out. So if I write the definite integral, I would say the definite integral from 20 to 140 of b of q, because remember when we did an indefinite integral, the function inside was a rate of change, and that value equals 360. So that is the total change in revenue. But wait, I chose the left-hand endpoint for each of those intervals. What kind of number would I get the same number if I chose the right-hand interval for each of those? Well, let's go back and look. If I choose the right-hand interval, I would have start off with 6 times 20 over this interval, and then the right hand of the next interval would be 4 times 20, plus the right side is 2 times 20, plus 0 times 20, plus negative 2 times 20, plus negative 4 times 20. So if I choose the right-hand interval, the end of the interval, I'm going to get a different number. And when you multiply everything out and add it together, you'll see that on this side, our total actually equals 120. And so on the other hand, I didn't just get 360, I also got 120. So we say that revenue increased between $120 and $360 over that group of sales. So it is between those two. In this segment, we're looking at a definite integral, and we start to look at Riemann sums, and we'll see what that means in just a minute. Certainly, we've been summing things up to find our total change. And in this problem, we're given data. We're given the rates R at which profit P changes over an interval of between 0 and 150 units sold. And we want to find our total change over that interval. Now, if I write that as a definite integral, I have the definite integral from 0 to 150 of R dq. So the rate R is what I'm looking at, and R is, of course, based on a quantity Q. It's R of Q, but it's not revenue. Remember, this is the rate of change of profit. Now, this data I've put on a graph. You can work with a graph. You can work with a data table. There are a couple different ways you can think about how you're working with the data when you're just given data in a problem. What I want to do is think about summing up the total change, like we've done before, based on an interval of Q. So when I'm going from 0 to 150, that's 150 units total. And I have 1, 2, 3, 4, 5, 6 units of data, 25 units spaced each. So if I divide this by 6, I'll get my 25 units. Or you can think of dividing your 150 by the 25 units apart gives us 6 intervals that we're working with. You can think of it either way for this problem. So my change is 25. That's my change on the interval for my data. So we can say that delta Q is 25. That is the change in Q. And notice the DQ. They go together. So let's set up our sum. My total change in profit is going to be, let's start with the left end of my interval. So between 0 and 25, I'll pick the left end, which would be 50 times 25. It's 50 is the rate of change of profit, $50 per unit over this interval of 25 units. Plus, for my second interval, I'm doing the left side again, and that looks like 35 times the 25 units. For the next interval, I have, looks like 20 times 25, plus for the next interval, this is 5 times 25. When I get here, it's dropped down to negative 10 times 25. And on the last interval, if I choose the left side, this looks like about 25. So I'd have 25 times 25. So if I add all of these up, my left sum, we'll call it, is equal to 1,875. And that is dollars, and that's the increase in profit. That is the total change in profit over the interval from producing and selling 0 units up to producing and selling 150 units. Total change in profit. Now, we had one negative value here. Oh, you know what I did? That's the negative 25 right here. Sorry about that. That one's negative also. I went down to 25. This is still the sum. Okay? But I have 2 negatives, which means it's just a change in profit. Profit has decreased on these last intervals. Let's look at a different type of picture. I multiplied 50 by 25. If I create a rectangle that's 50 units tall, over my interval of 25 units, $50. The height is 50, the width is 25. That's what I have here. I have a height times a width. It's a rectangle. My next one was 35 units tall over the interval that took me up to 50. A rectangle. That's what a Riemann sum is. We're summing up the areas of rectangles. 20 times 25, 20 is the height over this interval. Notice that each time on the interval, my height comes from the left end point. For this interval, my height is 5. But then what happens to the next one? Suddenly I get on this interval, and when I choose the left end point, this is my height. It was negative 10 times 25. And my last interval, my height was the negative 25 over to here, and I don't use this last one at all because I chose the left end point. Now, we can't really have these negative numbers if we're thinking area, but because these lie below the axis, we can say, well, let's do the area and make it negative because it's below the axis. But we still have to consider that when we're doing a Riemann sum, it looks like areas of rectangles, but we have to make it the actual width and the actual height or depth of the numbers that we've got. So this is what our Riemann sum looks like. That was our left sum. I can do a right sum. And if I do a right sum, it goes a little bit different. Now let's look for a minute when I said I chose the left end point. Let's get real mathy here for a minute. I'm looking at values for Q, and I'm starting at this first, at Q equal to 0, and I'm going to call that point, that X value Q sub 0. I'm sure you can't see that. q sub 0. So my 50 was my value of the rate at the first number, q sub 0. And then 25, that's the width of this interval, from q0 to q1. My next number at 35 was the rate value at q sub 1, and I multiplied that by 25. And I continued. If this is q sub 1, this is q sub 2, q sub 3, q4, q5, q6. In this case, when I went over to here, my last number that I've got for my depth or my height was the R value at q sub 5 multiplied by the width of this interval, 25. So this is what gives me a left sum. I start on the left end point, and on the last interval, I'm still using the left end point. I don't use the last q value at all. If I switch to do a right sum, then my numbers are going to change. I'll still have an increase in profit, but I'll do the values on the right-hand side. And so I'll start at R of Q1 because that will be on the right-hand endpoint. So this time, if I do right-hand sums, my height will be here. And then on the right-hand side, my height will be here for that interval. And here, so that I'm looking at different values when I'm doing my multiplication. Here, my height will be down here already, from there down, this interval. Between these two, I have this is my height, so that's my rectangle, and here I use the last endpoint. So this is my last rectangle. So these are the way the rectangles are going if I use the right-hand endpoint. And in this case, still multiply each one by 25. But when I get all the way 25 to the end here for the right sum, I do use the value at the last endpoint. So I start on the right-hand side and use those values. When I add all of those up, what happens here is I get a negative 375 for the right sum. Because if you look and see, I have bigger rectangles down here than I have up here, so the total sum, the total change is a negative number, but it's not a loss. This is not loss. This is a decrease in profit. So my total change for my right sum is a decrease in profit of $375 over that interval when we're producing and selling between 0 and 150 units. So we talk about profit and loss, but this is a total change in profit. So the change in profit is a negative number. Profit is going down. We still make a profit. We still are getting money. It's just that there is a change in profit. In this segment, we're still looking at definite integrals and Riemann sums, but now, as you see, we're going to start looking with formulas. So I've written my definite integral from 1 to 5 of e raised to the x squared power times dx, and I want to estimate the value of this integral. Remember, a definite integral gives us a number, and it is an estimate, what we're doing now. This says use left and right Riemann sums with 10 subintervals. Usually in the lessons and in the examples, you'll be told exactly what you want to deal with, which means some skill with the calculator or Excel to find function values is going to be important. So let's see what all we need to know here. We want 10 subintervals. The interval we're looking at, though, goes from 1 to 5. So I have an interval that only goes from 1 to 5, and I need to fit 10 intervals in there. So I need to take my width, which is 4, so I can say it's 5 minus 1, And I want to divide that up into 10 subintervals. So that would be 4/10. Or you could write it as 0.4, either way. So since I'm starting at 1, I would go from 1 and I go 0.4 units over to here would be 1.4 because this is the change from the first value to get to the next number. So I set up all my numbers. When we've had data before, we've been easily able to see what the change was because it was a data table that told us 20 units apart, 25 units apart. Here everything is 4/10 of a unit apart. 1.4, my next value over here would be 1.8, 0.4 plus 8. 0.4 plus 1.4 is 1.8. And then we have to, basically we need a data table. Even if you have a formula, you need data because we'll be adding up the function values. So we need to find e to the, depending on if it's a left or right sum, 1 squared, e to the 1.4 squared. This can be tedious, and especially with 10 subintervals. So what we want to do here is look at how you might set it up and then decide if you actually just want to put it in Excel to make it a little bit easier. So I need left and right sums with 10 subintervals. This is my delta x, 0.4 or 4/10, either way. And I need all these values. So let's see how we might set up a table of data. With 10 subintervals, I think I'm going to go down because I run out of space both ways. So let's look at our x's. And I start at x equal to 1. And then I want to get to 1.4, add 4/10 to the next one, also 1.8. So my intervals are in between here. And each time I'm adding 1.4 to it. Now, if we want to do that part in Excel, the easiest way to get this to work out is to say, okay, let's take this first number, and when I get to this cell, 1.4 is the same as if I write equals, let's say this is column A, and this is row 1. This would be in row 2, that's A2 plus 0.4. And this is exactly what I would put into the cell. I would hit enter and I'd have 1.4 because it would take 1 and add 0.4 to it. And if you then highlighted and clicked and drug it down, you'd have 1.8, and you could keep dragging until you got all the way down to the numbers that you need. This plus 1 plus 0.4 would give me 2.2, and so on, and I should end up at 5 if you drag it down correctly. This gives you the most exact values because I could have put in the fraction 4/10 here. It's in a formula, it would work fine. Remember, formulas start with equal signs. Now, the way to set up a table, let's say we're in Excel, if I go to column B, I'd want the function value f of x. So I'd want to put e raised to the first power. Well, I know that e to the first power is 2.71828 and some other stuff after that. Okay. It would be really good if we didn't have to estimate these values, so put in as many decimals as you possibly can. I think there's another 2.8, and after that, I don't remember what comes next. If you use a calculator, it will give you a lot of decimal places. Use as many as you can. Here, I want to do e to the 1.4 squared. Well, I don't know what that is, but I know that it would be e raised to the power 1.4 squared. So I would square 1.4 and then take e to that power. Well, the easiest way to do that truly is in Excel because it's so easy to just click and drag down. So for this, I'd start with the equal sign. I'd put the exp for the exponent part. And I want x squared. My x here is in cell A3 because this was 1, 2, 3. And I want it squared. This would give me my value, which is something like 7.09932, something like that, 7 point something. So this is what I get if I put in 1.4. So I have values for that. And since I have A3 here, I could do the same thing up here with A2, drag it all the way down to get my numbers. Now at 1.8, the value jumps up to about 25 point something, and at 2.2, it's already up to 126 point something. It's an exponential function, and the exponent is squared, so the values rise tremendously. But you keep going down until you get to the end, and then there are a couple things you can do next. You can put up a third column and put your delta x in it, which in our case is 4/10. So you could put a 0.4 here, 0.4, all the way down, 0.4. And even put another column in after that, that would be the product of your delta x times your f of x. If you decide to do that, you would want to multiply, what's this, column B times column C. The command here would be equals B2 times C2. And then you would drag that down and fill in all of your products. And once you've got the products, this cell is what we have before when we just take the function value times the width of the interval. Each time, that's what we have. So you get to the bottom of this column, all you have to do is sum up your values. And if you want to sum, go up a little bit. For a left sum, remember, we start with the first number in the interval. We would start with f of x sub 0 multiplied by our delta x. In this case, that would be 0.4. And then add up all the others until you get to the next to the last. Now, the next to the last one here would be not 5, but 4.6. So it would be the next to the last value. I'd start with f of 1 times 0.4, and I'd go down to f of 4.6 times 0.4. And I would add all those numbers up. Equal sum, this is this Excel command, D2, A, B, C, D, start with that one, all the way down to, I think it goes as far as D11, I think it's where 4.6 would lie, if you 2, 3, 4, 5, and so on. This would give you the values that you need. If you want to do a right sum, we would start with first interval, right-hand endpoint would be f of 1.4 times 0.4, and add all the way down to f of 5. That command would be equals sum. We started at D3, and then it would go to D12, one more of each. So I'd be looking at the right-hand endpoint. And when I do that, I find there is a difference between here. One of these sums is about 638 million, and the other one is about 29 billion. Big differences, big differences. And again, we saw that before. There's a big variation between right sum and left sum sometimes. So we will figure out more ways to get this more accurate in the future. But these are the values that we would end up with Excel. Be sure to check the examples in the lessons, because the Excel is right in the examples in the lessons while you're working with these.